let's get started. So, welcome once again to ECS. Oh. This class used to be called ECS 189H before it got its own course number. I guess the first time you teach a course, they like to give you like a trial run of it with this kind of temporary course number. There's all sorts of ECS 189s that you could take. But this actually is a real honest-to-goodness course now. So, but I haven't updated all the slides. That's besides the point. The point is, we're trying to talk today about how to align multiple sets of 3D surface data together. So what we talked about already in this module of the course, just as a reminder, this module is about how to manipulate 3D surface data, such as you would acquire from a radar detector, LiDAR, or sonar, or multi-camera system. And we have already talked about the kind of the technology of how the data is acquired and how you remove noise from it. So the next thing we're going to talk about are the two key technologies that allow you to actually do interesting things with that data. The first one is aligning pairs of these surface data sets together, and the second one is going to be extracting features from them. And you can, for the purpose of extracting features from them is to detect objects in scenes and build 3D models and that kind of stuff. So, and furthermore, when we talk about mesh alignment, we're going to spend 2 days on this. And the first day is going to be focused on rigid alignment. I'll describe exactly what that means, but it basically means that what you are trying to do is take an object that is rigid, like, for example, this table, take multiple scans of it and align those scans to each other. On Wednesday, we'll talk about the opposite of rigid alignment, which is deformable alignment, which is to say you have an object that changes its shape or its configuration in some way in between your scans of it. And so you want to align the two scans together partially by deforming one of them onto the other. So the classical example of why you would want to do deformable alignment is that you have you're doing an operation on somebody, you have cut them open, and you have a 3D model of their internal organ, let's say their liver, that you acquired before the surgery. But now here it is in the surgery, and it has been squished and smushed in various ways because they have been cut open. So you want to deform the pre-operative model to the thing that you're actually acquiring, or the thing you're actually seeing there on the operating table, which has been deformed in some way. But that's going to be on Wednesday. So, if you recall, I told you a couple of days ago that if you can align 3D meshes together, you can do some useful things, like locate yourselves in a map of the world, especially in a world where there's no GPS. You can take multiple scans of the same object, like this one, and align them together to build 3D models from multiple views. And then we can do this other thing that I described, which is to verify the fact that we have actually detected the correct object that we think we have detected in a scene by aligning a 3D model to a scan of a scene. And all of these things, the engine that is driving all these applications really is mesh-to-mesh alignment, surface-to-surface alignment. And intuitively, you all know what that means. It means to basically take one surface that's been taken from one point of view, and the other surface is taken from another point of view, and rotate and translate the one so that it lines up well onto the other in the intuitive sense. So here's the key components of this problem. Let's say we start with two surfaces. And by the way, anytime you see the word mesh, it's synonymous with the word surface, at least in my usage. So usually what happens, as I've told you, is that you collect data off of a scanner. And the form that it comes in is a set of three-dimensional surface coordinates, XYZ, 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 and that these are connected to each other by edges to form a discrete representation of a surface. And those surfaces, because they consist of points that are connected together with these lines, they're usually referred to as surface meshes. So let's say that we have two of these meshes, and I'll refer to those as A and B. A has points A1 through M, and B has points B1 through Bn. So they don't necessarily have to have the same number of points on them. But each one of these is a 3D point in some coordinate frame. Now, each one of those points is a three-dimensional surface coordinate. And for now, let's say that we call A the moving mesh and B is called the fixed mesh. And the idea here is that if we're aligning one mesh to the other one, we can basically keep one of them still and move the other one and move it around so that we can try to align it to it. There's no need to think of the problem as being simultaneously moving the two surfaces at the same time. So what I'd like to do is similar to the object detection problem, I'd like to give you a recipe or a set of design decisions that you, the user, need to consider if you are trying to put together a system for surface-to-surface alignment. So one of the components, or one of the design choices that you have to make is what kind of geometric transformation model are you going to use? So a geometric transformation model is a function, t, that takes 3D coordinates as input, modifies those 3D coordinates in some way, and provides an output that is also 3D coordinates. So if you have a point A sub k, which again is just going to be x, y, z, and a vector of parameters, which we call a theta, that tells you what the behavior of the geometric transformation is, then you just get a new x, y, z coordinate a k prime. So the parameters that govern how this geometric transformation work are called theta. I'll just say that it's a vector of parameters. So let's just take one simple example where our geometric transformation model is simply a translation. And a translation just means that you take one mesh and you slide it in the x, y, and z directions to some degree. Then in that case, our vector of parameters theta is going to have 3 entries in it, which tell you how much to translate in the x, y, and z directions. And if I have one particular x, y, and z translation, I call that t, x, t, y, and t, z, then this function t is going to take a as an input, a k x, a k y, a k z, and simply add the t's to it. So then the input's going to be the original a coordinates, and the output is going to be the a plus t coordinates. So this is a simple, very, very simple transformation, geometric transformation model. But the point is that all it does is it modifies 3D coordinates to give you new 3D coordinates. Okay? The next thing you're going to need, and this is often the very, very tricky part in realistic settings, the next thing you need is what's called a metric. So the idea here is that let's just say we have a hypothetical geometric transformation that we think aligns two surfaces A and B together. Or let's say that we propose one. You can propose one at random, and you want to just get a sense of how well it aligns the two surfaces to each other. You want to evaluate that in some way, and you want to evaluate it numerically. So that if you had two identical versions of the same surface, and you got the geometric transformation just right that nailed it so that all the corresponding points perfectly overlapped with each other, you would want to get a numerical sense of the fact that it's perfect. So for example, you might want to have a function that gives you a very, very low value if you do nail that geometric transformation and get it perfect. But meanwhile, if you get the geometric transformation perfectly wrong so that they're totally not aligned with each other, you might want the value of that function to be large. And that's what the metric does for you. In some sense, this is the recurring problem we have of taking our semantic notions of what we want our system to do and stuffing it into mathematics. This is kind of a recurring theme. So in different settings, depending on what your meshes look like and exactly what you want to emphasize about how well they should align with each other, you might have different ways that you could quantify this sort of goodness of fit. That's another term for the metric, is that it's a goodness of fit measure. So the metric takes our moving mesh, A, and it moves it by applying a particular geometric transformation to it. So this is the output of applying t to all the points in A, where t's behavior is governed by the parameters theta. and it also takes B, which is our fixed mesh, as an input, and it maps these two guys to some real number. And usually what we do is we restrict this to the set of positive real numbers, so that the minimum of m is 0, and the maximum is either infinity or it's some fixed positive value. And the notion here is, like I just said, if the transformation T, which is governed again by theta, aligns A to B well, then the value of m should be minimal. It should be close to 0. If it fails to do so, then the value should be high. So this is m. And we will describe each of these components and how you can design them, how you can actually implement them after I describe what all the components are. So then the next thing is, we've seen this before, I think, an optimizer. And an optimizer is basically a numerical scheme or a numerical strategy for finding values of theta, which is to say, finding geometric transformations that minimize the metric, given that you have some initial guess at what the geometric transformation is. So it could be that you have absolutely no idea a priori before you start analyzing the data of what the transformation might be, or even what the ballpark of the transformation values should be. So in that case, you can just initialize this theta to whatever you want, to some random values. But oftentimes we do have at least a little bit of a notion of what the transformation is that aligns two meshes together. And just as one concrete example, imagine that we're back in our vehicle, say our Humvee, that is rolling through the desert trying to figure out where it is on a large Landsat map that covers the entire area. And basically, imagine that you align your surface data to that larger map at one location and then drive a little bit and want to do it again. Well, from the odometer, you can get a sense of how far you have traveled in between those two. So based on that, you have an initial sense of what the geometric transformation might have been from your original mesh that you started with to the current one, in case you wanted to align those two together. And similarly, there was kind of a period of time in 3D modeling where every 3D scanner came with a turntable. And the turntables had motors with encoders on them, so you could actually tell how much the turntable had rotated. So the idea is that you would get a 3D scan of your object, rotate it by some fixed amount, take another scan, rotate it again, take another scan. So in between those scans, you had a pretty fair idea of what the rotation was between the object when you first took a scan of it and the object when you second time took a scan of it. So you can use those as your initial guesses for what the transformation is between the first scan and the second one. But as I've said, this is not essential. You could maybe have no idea at all what the transformation is between the two. And furthermore, even if you have no real guess at what the initial transformation is, you can do some kind of tricks that'll get you closer to the right solution. So if I take two scans of the same object, but I have no notion of where the viewpoints were in both cases, then I can do something simple like translate the two of them so that their centers of mass align with each other. And then I basically have reduced the problem to more or less finding a little transformation and possibly a big rotation. And also you can use mesh feature vectors, which we're going to talk about after we talk about alignment, to get another initial sense of what the geometric transformation is. Okay, so at that point, are there any questions about the sort of the design choices or the components that you need to worry about if you're going to align 3D meshes to each other? Okay, great. So here's another example. Let's say that T is a rigid body transformation model. We talked about, when we talked about invariances, we talked about image patches or image features being invariant to different kinds of geometric transformations. And I told you that the simplest kind of transformation is one that rotates and or translates your image patch. And that's called a rigid body model. So this is the simplest, or not the simplest, this is another example of a transformation model. So here our vector of parameters that governs the behavior of the geometric transformation has 6 entries in it. 3 translations along the x, y, and z directions. And then you can think about it as being 3 rotations, 1 around the x-axis, 1 around the y-axis, and 1 around the z-axis. So tx, ty, tz, rx, ry, rz for translation and rotation respectively. And it does what you think it does. It rotates the object by the degrees given by rx, ry, rz, and then it translates them along each of the axes by tx, ty, and tz. So, as you can imagine, I briefly discussed this, but just to reiterate, this is appropriate when we're aligning 2 scans of the same object that does not necessarily change its conformation or change its shape or change how it's configured in any way in between the scans. But it's also common to want to align scans of objects that are slightly different from each other, such as the liver, like I told you. So, roughly speaking, today we're going to focus on the rigid body case and techniques you can use for that. And then on Wednesday we're going to talk about the deformable case, which is, like I said, typified by the liver example, where you really want the geometric transformation to deform the object as you are aligning it. That got cut off at the bottom. Sorry. So, just as a rule of thumb, the deformable or non-rigid transformations tend to have a larger number of parameters in your parameter vector. And that's because if you think about it, a deformable transformation is something that is more complicated than a rigid one. It's not just changing the position of the object and the global orientation of the entire thing, but it's also bending and stretching and contorting and twisting each part of it individually to some degree. So it should be intuitive that the deformable transformations are more complicated, they require more parameters, and usually, this is just a rule of thumb, but usually they are harder to estimate. And just as a broader rule of thumb, if you have a problem that is formulated in terms of finding a good set of parameters, and the number of parameters is larger, then that problem is usually harder. Fewer parameters you have, more or less, a lot of the times it's easier. Any questions? Okay. So, let me just fast forward a little bit. Yeah, right. Okay, so let's say that I have postulated that there is a particular geometric transformation, a translation and rotation, that aligns mesh A to mesh B. So then I have this problem of quantifying the degree to which they seem to agree with each other. So for surface meshes, there seems to be a fairly intuitive way to do this, which is driven by the fact that you have a bunch of points that are connected by edges. So in particular, what you can do is have each point on your moving mesh, or each point on your fixed mesh, it doesn't really matter that much, and have each one of them tally their vote or contribute their opinion to some degree about how well that particular local location of the mesh seems to align with the other mesh. So what you can do is, if the green one is the moving mesh and the red one is the fixed one, kind of doesn't matter which one is which, but what you can do is basically take the moving mesh, take each point, and calculate its distance to the closest point on the fixed mesh. So that's going to be some distance. Now, if these two meshes align with each other perfectly, that distance is going to be close to 0, especially if these 2 points correspond to the same thing on the object. So what we do for point-to-point distances is we simply take each point on the moving mesh, calculate its closest point distance to the fixed mesh in terms of point-to-point distance, and add those up. So the larger that thing is, the worse the alignment is. And if it's closer to 0, then they seem to align with each other perfectly. Fair enough? Now, there's a little bit of a problem here, which has to do with the fact that we are discretely sampling a continuous surface. So what I mean by that is that if you are taking a scan of my lunch bag here, the object itself is filled in. It's not like Swiss cheese where there's holes in between parts of the surface. And yet, what you are doing when you take a scan of it is taking this continuous thing and converting it into a discrete set of point samples. And in fact, when you're doing mesh-to-mesh alignment, you're doing this twice. You're getting one discrete sampling of it for the first mesh and a second discrete sampling of it for the second mesh. So there is a chance that you could scan a point on the lunch bag in the first mesh, A, and not scan that corresponding location in the second mesh. So this is a bit of a problem because, as I've said up here, we're going to formulate our goodness of fit in terms of how close each point here is to a point here. Well, an obvious workaround to this is to simply get which points on these faces or on these edges is closest to the point on our moving mesh. So basically what we do here is we take a perpendicular projection of this point and we shoot it onto the fixed mesh and see how far this distance is. It's just a little bit of a tweak of this idea of point-to-point distances, but it can help us get around this problem that we are taking two discrete samples of the surface that might or might not correspond to each other perfectly. And then if you really want to go kind of hog wild, you can, in fact, instead of just taking point-to-point distances or point-to-surface distances, you can actually sort of raster scan each one of your faces of the mesh, which is made up of a set of edges. Raster scan it and then get distances between all pairs of surface positions on the moving and fixed mesh. So this is kind of like what you're trying to do really is approximate the integral of the closest point distance over the entire continuous surface for A and B. And this is kind of as close as you can get to doing that, given that you have a discrete sample of it. Does that make sense? Now, the devil's in the details with metrics, it turns out. And you will learn about this in the second homework assignment, which hopefully you are all going to start working on quickly. We need to worry about mesh resolution. So I've already alluded to this by saying that each surface is a discrete sampling of something that is continuous. But the problem can be extreme, especially since we usually get a very large number of points out of the scanner. And the first thing that we do is simplify these. We'll talk about mesh simplification later, but it's very often the case that if you have a planar surface, something that's more or less flat on your object, and you scan it twice, sometimes you can get a point that's right in the middle, and maybe sometimes you won't. And yet, what I've told you, at least for some of the techniques, is that what you do is for each point, have it contribute its opinion to how close the other surface is. So for this one, the fit seems pretty bad because its closest point on the other surface is way over here, when in reality it's actually not that far away at all. So that's one reason to use a point-to-surface or a point-to-plane distance as opposed to a point-to-point distance. You also have to worry about outliers. So if the only thing that I show you on this, in terms of these two surfaces, is these three pairs of points, it should be very clear that those two surfaces correspond to each other really well and that they align quite nicely. But now, let's say I add that additional point to the moving data set. Then suddenly we have a problem where intuitively we all know that these two surfaces probably align with each other really well. But now there's this extra thing saying, no, 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 the fit is actually quite terrible because my closest point on the other surface is this one, and it's really far away. This happens all the time, and in fact, there's no way of not observing this problem if you're going to do mesh-to-mesh alignment for the purpose of 3D modeling. Because the whole point of doing mesh-to-mesh alignment for 3D modeling is that you have two views of the same object where the viewpoints overlap to some degree so that you can align them, but they don't overlap 100%. Because what you're trying to do is basically build up your object model by taking multiple scans of the same object. So basically what's going to happen is that your A and your B are going to overlap to some degree, but sort of the pinky fingers part of it are going to not overlap at all, but that's kind of the point. So the question is, what should these pinky finger parts tell you, or should they vote at all about how good the alignment is? And the answer is probably no. They're more or less outliers, which is to say that there is no point on the red surface that really should correspond to the green point here. So this green point should really just kind of shut up and not say anything about how good the goodness of fit is. And in the second homework assignment, you will explore ways to make that green point shut up and not give its opinion. Okay? So the other thing to worry about on a very practical level is that while it should appear obvious, well, I've kind of provided my opinion that this bottom way of doing things here, surface-to-surface distances, is really preferable, because it's your best possible way of getting around the problem of discretely sampling the same surface twice with the samples not necessarily corresponding to each other. The problem is it's very expensive. So if you think about it just intuitively, or just kind of a back-of-the-envelope calculation, the top way of doing things are just calculating point-to-point distances. Let's see, for every point on the moving mesh, you have to find, let's say that you're not smart about how you calculate distances. What happens is that for every point here, you want to calculate its nearest point on this data set, which in the worst case means that you have to calculate a distance between this guy and all the other points on the red surface. So that's not how you would do it in practice, because you can actually be more efficient about how to do this so-called all points nearest distance problem, which is to say for all points in the green, you want to find the nearest point on the red. But that's sort of your worst case. The worst case here is a little bit different. What you have to do is for each point, cast a ray in some direction, and then for every face on the red surface, determine how or if that ray intersects that plane. And furthermore, you need to be smart about the shape of the object, because if this red surface wraps around and the ray intersects with a plane that is way down here, what you want to do is detect the fact that this one is closer. So you have to do more or less computer graphics type of calculations that ray casters use to calculate whether a ray of light has intersected with a plane on an object in the real world. So that's expensive too. This is even more expensive because you're doing all the operations you did for this one and more, because as I've said, you're raster scanning each one of these faces and shooting more and more rays even in the middle of these faces too. So that's why that thing at the third choice, which is true surface-to-surface distances, can be very computationally expensive. Anything about metrics? Okay. So I've described optimizers in the past as being something like the black art of many of these image processing problems. You have a well-defined problem that you want to solve, which again is to find values of your parameters theta, which minimize this metric, where the metric takes as input the transformed moving mesh and the fixed mesh, and you're given some, let's say you're given some initial guess too. There are ways to optimize this thing. And a couple of them include the following, which I should mention that none of the three that you see up here are specific to image processing. Basically, there's a whole community of people who do, numerical optimization for a wide variety of problems that do or don't involve images. And they develop algorithms for solving exactly this kind of problem. So what gradient descent techniques do is that they, as the name suggests, descend a gradient. So the idea here is that you calculate the gradient of m, and in fact what you usually do is approximate the gradient of m, or approximate m in some way locally, depending on where you are in terms of your initial guess of the parameter vector. You compute the gradient of that thing and then iteratively move theta values towards values where that derivative equals 0. So if you remember back from calculus, if you plot a function, at its minimum and maximum is where the derivative goes to 0. So here all we're doing is starting at some initial position in our function and moving towards the derivative equals 0 direction. We're kind of going downhill. And there are variants of this gradient descent idea, including steepest descent and conjugate gradient, but this is the general idea. And the trick here is how you calculate the gradient of the metric. It might or might not be clear how to do so. In fact, the way I've described the metric thus far, it's not all that obvious, right? So how exactly would you take something like find my nearest point on the other surface and get the distance, and turn that into a function that you can take the gradient of? You actually have to do some bending over backwards to get that to happen. trust region techniques are a little bit more complicated in that you do a kind of a higher order approximation of this metric function. So usually what you would do is approximate the metric locally by something like a quadratic curve, and then move the parameter values towards a minimum of that thing. And Gauss-Newton is your prototypical example of this kind of trust region method. And then hybrid methods do something that's in between. You either in some iterations do a complicated approximation of M, and some other ones you do a planar approximation, or you mix the two together in some way. Now, the methods called simplex methods usually just do away with gradients. So we're going to assume that we aren't able to actually get a good estimate of the gradient of M at any particular location theta. So for simplex methods, simply what you do is try multiple values in a neighborhood and see how that neighborhood looks basically by walking around. And in particular, what you can do is say, well, I moved the parameter values a little bit in one direction, and the fit got worse. M got higher. And then I moved in the other direction, and the fit got better. M got smaller. So why don't I move in the direction where M got smaller? That's kind of the simple intuition of simplex methods, but in higher dimensions where you have 6 parameters, this gets a little bit, you have to do some reasoning about the geometry of it. And so Powell's method, downhill simplex, and bisection are all different specific simplex methods. And in fact, kind of empirically or practically speaking, a lot of times this happens where people start by trying to find a good minimum of M using gradient-based techniques, but the gradient is noisy, which is to say the gradient seems to have a lot of little tiny local minima. So to get around that, they'll use simplex methods instead, which basically take these hops that try to get around the local minima, and they don't try to approximate the gradient at all. Then finally, there are these things called stochastic methods, which is something like taking a random walk or a semi-random walk. So given an initial set of values for your parameter vector theta, you sort of take a random leap to a new location and evaluate how good the goodness of fit is there, how low M is. And a lot of times what happens, especially for methods like simulated annealing, what will happen is that if you hop to a new location and you've made your goodness of fit better, then there's a high but not exactly certain probability that you will stay at that location. So the thing that makes it stochastic is that, crazily enough, even though you move to a better solution, you might actually move right out of that solution or go back to the old solution. But the fact that it's stochastic and that it's not completely determined that you always go to a better value, that's the thing that actually allows you to hop out of some local minima. So which one to choose is really difficult. The gradient type methods are fast, but they have these problems with getting stuck in local minima. And this is a very good example where all a person has done here is taken one 3D surface, duplicated it so you have exactly the same surface before and after, and then evaluated a closest point metric before and for many different values of a rotation. So this person kind of canonically rotated the moving data set by 1 degree, 2 degrees, 3 degrees, 4 degrees, 5 degrees. And for every one of those degrees, it evaluated M, the goodness of fit, which is to say how close the closest points are between the two surfaces. So what you would hope is that at 0, 0 should be the best, right? That's where the two surfaces perfectly are aligned and correspond to each other. And what you would hope is that the goodness of fit gets gradually worse and worse and worse and worse and worse as you get further away from this correct solution. And if it did gradually get worse and worse and worse, then you could have hope of using a gradient descent type method. And the reason why is that if you started way over here and you knew that the solution went gradually down, 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 then you could simply follow the gradient and go step, 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 step towards the right solution. But clearly that's not going to work here. Because if you start, for example, right here and do gradient descent, what's going to happen is that you're going to stop as soon as you get to some minimum value, which is right here, which is wrong. And even if you start here, you're going to go down, 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 which is a little bit better, but it's not all the way to 0. And similarly, over here, things are even worse, because if you start not that far off from the solution over here, you're actually going to go further away from it, because you're going to follow the gradient downwards away from the correct solution. So this is why a lot of the times gradient-type methods don't really work very well. And the response to making a graph like this and saying, uh-oh, gradient-type methods don't really work, there's usually one of two different responses to it. One is to get yourself a new metric, so that when you calculate this function m over a set of different rotation angles, for example, it does end up looking more smooth. And the other response to getting a graph like this is to get a better optimizer, which should be clear. If an optimizer is able to hop around in this space so that it eventually finds this solution without having to follow the gradient, then you're in business. Any questions about this? Okay. Now, the trade-off is really kind of a straightforward thing, where gradient-type methods are fast but prone to these kinds of errors. Simplex methods take longer because you're basically evaluating the function several times as an alternative to calculating the gradient. And stochastic-type methods are really slow because you're basically, as I've said, bouncing around and moving the parameter vector to positions that may or may not be relevant, but it tends to get around these local minima type problems. Okay, so just a couple of announcements. Oh, that's not right. Sorry. Wednesday. Why did I put Wednesday? Friday. No. Oh, I know what happened. Yeah. Okay. This is last year's version of these slides, and I thought I modified it. I didn't mean to give everyone a heart attack by saying you have a midterm on Wednesday. Midterm is November 1st. Homework 2 is posted and available for you to start working on. And for those of you who did not get homework 1, what's wrong with my typing today? 20%. Well, okay, I can just say you get 80% of the points you would have gotten. So you take a 20% hit off of your point total, basically, if you turn in homework 1 by this coming Friday. Any questions about administrative items besides these? And, oh, there's one other thing. Well, it's kind of pointless to put it in the slides at this point because it's about to happen, but I posted an announcement to SmartSite today saying that my office hours are 3 to 5 today. So sorry for those of you who are going to go straight from here to office hours, but I have a thing that I have to do at 2, so I'll be there in that office from 3 to 5. Yeah, use the mic, please.
Do you have any practice midterms online that we can take a look at how your midterms actually look, or is it just kind of come and take a test?
I don't have any practice midterms online. But basically the format of the exam is going to be, first of all, you need to know the lecture slides. I think a lot of people have complained in the past that they studied really hard on the supplementary reading when really the exam questions are going to be almost like cut and paste out of the lecture slides, pretty much. How do you do X? And I had a slide that said, to do X, you either A, B, or C. So that's your key thing, and it's also going to kind of probe your problem-solving skills. So how would you do this? What are 2 different ways to solve the following problem that we talked about in class? Any other questions? Okay. All right, so let's talk about one of the really most well-known 3D surface processing algorithm is called iterative closest point. In fact, it's very common if you talk to someone about their 3D surface data processing system for 3D modeling. A lot of people will nonchalantly use this acronym and say, oh yeah, well we used ICP to align the surfaces together. So here the transformation model is rigid body transformation, which is, just to remind you, consists of 3 translations in the x, y, and z directions and 3 rotations about the x, y, and z axes. And the metric is the traditional closest point metric, which was at the top of that slide that I told you about. It has all of those limitations that I told you about. But this is the basic algorithm. And the metric is to simply sum up that closest point distance over all points in the moving mesh. And the optimizer takes a kind of a step-by-step approach, where in the first iteration you identify the point on the fixed mesh that is the closest point of your point on the moving mesh, and you do that for all points on the moving mesh. And then there's a closed form solution for finding the transformation that minimizes the sum of those distances for that particular set of correspondences. So really what you're doing is that you're taking every point on the moving mesh, assuming that it corresponds to the closest point on the fixed mesh, and then finding the transformation that minimizes that the sum of squared errors between them. So this is both the intuitive thing about ICP, and it's also where it gets into problems. Because a lot of times, if the initial transformation is really off, then very few or none of the points on the moving mesh are actually supposed to correspond to their closest point on the fixed mesh. But yet, ICP is going to try to align those together. The upside, in terms of computation time, is that there's a formula by Berthold that was kind of independently came up with by Berthold Horn and Martial Hebert that gives you a closed form solution that is fairly fast to compute. Given that you have given that you have correspondences between one mesh and the other, it'll give you the rotations and translations you need fairly quickly. It's basically a matrix decomposition. It's all linear algebra. The other thing you can do is do gradient descent on M, which will. The reason why you might want to do that is that you might want to actually sort of move in the direction of finding of the transformation that aligns those 2 sets of points perfectly without actually making the leap of going all the way there. So then we just keep doing this. We find closest points, we find the transformation, we transform the mesh. Then we again find closest points, and then again transform the mesh. Then we again find closest points and again transform the mesh. Now, I've just told you what the limitations of ICP are. So over the years, there's been a whole literature of kind of ICP pluses, of ways of improving the method by improving either the method, or either the metric or the optimization. We've actually talked about a couple of those already. So there's different ways of sampling those 2 discretely sampled surfaces so that you don't have those problems with outliers and so on. Ways of finding correspondences and weighting the correspondences. So this is what you're going to do in the homework assignment, actually, is find ways to weight the correspondences so that some of them have higher weight and some of them have lower weight. And then outliers, how to say, again, that points that are very far off that have no corresponding point on the fixed mesh should not offer their opinion about how good the transformation is. Right. So the problem of outliers and the problem of finding correspondences can be thought about as finding a point on the other surface. So for every A sub k, finding a point B sub c that it's compatible with. Not just that that the B point is close spatially to the A point, but that they are compatible in some way, that the local surface shape or the local surface characteristics kind of look similar between those corresponding locations. And in particular, you can say, well, this point A should only match the point B if the neighborhood of the surface neighborhood around there looks similar in terms of surface normals, curvatures, or some other property such as its color or material properties. Some of which you can actually acquire from laser radar, in fact. You can't get the material properties directly, but you can get actually some sense of the color of the surface. Another idea that comes into play in terms of determining whether A should correspond to B and how heavily you should weight that correspondence is the idea of simple sampling, of stable sampling. So let's say I have two surfaces that are like this. And it should be obvious, and let's say that all we're concerned about is finding a translation in 2D, so translation in this direction and in this direction, that aligns the two surfaces to each other. Now, without actually having this particular example, it would seem like a really good idea to have your correspondences cover as much of the surface as possible. So if the entire moving mesh is covered by points where you have a match between that and the other surface, that would seem to give you your best sense of how you should align the surfaces together. In other words, you would be the most confident in that set of correspondences. Well, this is a counterexample to that. So in the top case, we have correspondences between each of these points in the moving mesh and the correspondingly shown points in the red mesh. And yet, we can slide the moving mesh in any direction, not get a better or worse match. So if we move the green mesh so that it's right here, then we'll always get the same point-to-point distances for basically all positions of sliding it to the left and the right. It'll basically, each one of those translations will look like it's a perfect match. Meanwhile, if our only correspondences are right here, then that'll constrain the transformation both in the x and y directions. Anyway, if you move the green surface so that it aligns to here, then any way you move the green surface is going to give you a worse answer than the one that's suggested right there. So this is another way of saying that that some correspondences are extremely helpful and other ones are not. And that we should try to determine which correspondences help us to constrain the transformation and which ones kind of are ambiguous about some of the transformation parameters, such as the sliding from left to right. So here, let's say that we have another construct called C, which is this matrix. So let's say that M is going to be the closest point, well, either point-to-point or point-to-plane distance for some A of K. So it's going to be the distance from A to B at that point. And that M is going to be this metric that we think is intuitive, which is basically the further the distances are from, the further the points are from each other, the worse the match is. So that's going to be M. So let's say that we take the derivative of that M with respect to the transformation parameters for every possible point. So the way to think about this is that we have a correspondence between AK and BC, and if we align the surfaces so that they align well with each other, what happens if we slide the surface in one direction or another? What happens if we rotate the surface while respecting that correspondence? So that's going to give us our derivatives of the metric with respect to the transformation parameters. Or just to repeat that a little bit, let's say that I have my initial transformation and I slide it in one direction. Did the metric actually get worse? And if it didn't, then that's basically another way of saying that we don't know whether we should slide or not. It's sort of it's an uncertainty. So if this C is full rank, then it tells you basically that your transformation is really well constrained. You can't very well slide the moving surface around and still get a good match. The goodness of fit goes down. If it's not full rank, then that tells you that you basically have a gauge freedom, that you can slide or rotate one surface with respect to the other and still get pretty much approximately the same level of matching, which is not what you want. So I'm going to skip that and just go straight to the results. What's been done here is that every point on this bunny surface has been labeled with how certain of correspondences it provides. So points that are red are like the humps on the previous example, where having a correspondence at that location really constrains how good the match is from one to another. And points in green, not so much. Whoops. And if you look at this, it might be intuitive why that is. You can basically slide the ear in this direction and still get an equally good match for these points. And also you can rotate about the ridge on the ear and still get the same goodness of fit. So there's ways to speed it up. You can read that yourself. For mesh alignment, just to summarize, you need two meshes, a transformation model, a metric, an optimizer, and initial conditions. And we talked about the prototype algorithm for doing that. It's called ICP. Any last minute questions? Okay. Again, office hours are 3 to 5 today. Oops.